So, yeah. So we're recording now. Yeah, everybody chill. Okay, so we'll see how this new camera, which is currently swinging back and forth, will actually work for us. All right, kinematics formulas. Let me explain what kinematics formulas are used for. When we talk about kinematics, we're talking about things that are in motion. And if I take this ball and I drop this ball from anywhere, gravity's going to grab it and pick it up and it's going to move faster, right? So it's going to move faster over time. And that speed that it picks up, v, can be given to us with a formula. Velocity, or change in velocity, equals acceleration times time. In other words, every second that gravity is pulling on this, gravity is going to increase the speed of this ball by a set amount. Pretty much no matter where you are on the planet, it's going to be the same amount. And we know that gravity accelerates things according to a certain value that we call g, which ends up being negative 9.8 meters per second squared. In other words, the meters per second squared comes from meter per second, that's velocity, every second. Every second, gravity is going to make this go faster by approximately 10 meters per second. After 1 second, when I've dropped it, it's going to be traveling at negative 10 meters per second. After 2 seconds, it's going to be traveling how fast? Throw it out there. Negative 20 meters per second. After 3 seconds, how fast is it going to be traveling? Yeah, negative 30 meters per second, and so on. Okay? So as we look at the velocity of something that gets dropped over time, gravity is going to make it go faster by 10 meters per second every second. Does that make sense? Yes? No? Okay. So when something is falling, when it's in what we call free fall, gravity is going to grab onto it, and it's going to go faster by 10 meters per second every second. By contrast, if we ignore friction on the table, and I roll this ball across the table, if I ignore friction, what's happening to the speed as it travels across the table? It's constant. It has a constant speed. If I give it a push, if we ignore any kind of friction, it's going to have the same speed as it travels across the table. So, the velocity of something just traveling along is pretty much constant if there's no gravity. Does that idea make sense? So, if something is constant, or if there is no acceleration, velocity is going to be constant. Next. What about the distance these things cover? And that's what we really want to think about. The distance something covers. Well, if I was to roll this along the floor and there was no acceleration on the ball, the velocity was constant. After, let's say I roll this at 1 meter per second. That means every second it goes how far? 1 meter. So after 2 seconds, how far is it gone? 2 meters. After 3 seconds, how far is it gone? After 4 seconds, how far is it gone? Okay, so the formula we can use for distance, if you want to know how far something goes, distance, we're going to talk about displacement later, distance is based on a velocity, and what else? How far something goes is based upon what? Velocity and time. How fast you're moving and how long you're moving. If you're traveling 60 miles an hour, you travel 1 hour, you would expect you to go 60 miles. Okay. D equals VT. So far so good? That if there's no acceleration. So here again, no acceleration. But what if there is acceleration? Now we have an interesting discussion. If we do have acceleration, can we use this formula? No. Why? Exactly. The velocity is changing. So the velocity is getting larger as we fall. So what velocity would you choose? So if it is falling, we use my favorite formula, the triple F. It is the free fall formula. And the free fall formula looks like this. 1/2 AT squared. 1/2 AT squared. In other words, it is now, when something is falling, its distance is determined not by velocity, but by acceleration. It is acceleration that's changing the velocity, AT, but acceleration is changing velocity as velocity changes distance, so we need a square in there. If you have your calculus, if you've been in calculus and you recognize these are, it's a very famous derivative. Derivative of x, 2x, x squared, okay, and anyway, moving on. Okay, so that's the free fall formula. D equals 1/2 AT squared. If you drop something, it's going to travel a distance based on the acceleration it encounters and how far it's fallen. If you throw something and there is no, roll something and there is no acceleration, it's going to cover a distance equal to velocity times time. So what if you throw something down? You're going to use both formulas. If you throw something down, you give it an initial velocity, and it's falling, you're going to use both formulas. And the formula looks like this. D equals Vt, there, plus 1/2 AT squared. This is our primo kinematics formula. Yes?
So what's this formula for again?
If something is falling, you can determine how far it's going to fall using D equals 1/2 AT squared. If something is thrown, you can determine how far it moves by Vt. But if something is thrown and falling, you simply add the two together. So if something is thrown and it's falling, you're going to add the two together. Now, for the next couple weeks, we're going to focus, actually, next week, we're going to focus primarily on things moving in one dimension. Middle of the month, we'll add a second dimension. We'll launch things with projectiles. But for now, we're going to focus on things traveling straight up or straight down or only left or right. So far, so good? So here's our first formula. How much faster does something get when it's being accelerated? Delta V equals AT. How much faster is something going when it's being accelerated? Delta V equals AT. If something isn't being accelerated, its velocity is going to be constant. If something is not being accelerated, the distance something's going to cover is given by D equals Vt. If something is being accelerated, the distance it's going to cover is 1/2 AT squared. And if something gets an initial velocity and it's being accelerated, then D equals Vt plus 1/2 AT squared. Okay. I can see we're losing you, so we're going to move on to something else. I just want to know if there are any questions with what I just put out there. Okay. Now, all of these have a time component, except for the velocity when it's constant. Someone got together and they did some algebra, and they put these formulas together, and they came up with a sixth formula, which is really handy if you don't have time. Because, you know, like system of equations where you can take one thing and add them together and get rid of a variable? You can do that, and the formula that you get looks like this. Vf squared equals Vi squared plus 2 AD. Yep. The square of an initial velocity plus 2AD will give you the square of the final velocity. Notice there is no time in this sixth formula. That is the formula you can use if you want to, if you don't have time. You never need to use this formula, but it's a fun little shortcut.
I'm confused on the last formula you just put up.
This one?
Yes.
Okay. Are you confused about how it came to be or what it means? Okay. So how it came to be was taking these 5 formulas and doing a systems of equations, basically putting everything in terms of t. So if we say t equals d over v, and we replace t with d over v, and then do some algebra, this is what falls out. Okay. I tried to do it really fast during passing period, but I realized it was going to take longer for me to demonstrate it than I had it during passing period. So right now, there's just some hand waving. Woo, math! This is what ends up. So if you take all these formulas, woo, math, you can illustrate all 5 formulas with this formula. Vf squared equals Vi squared plus 2AD. And what it means is, if you know how fast something is going, to begin with, its initial velocity, and you know its final velocity, but you don't have time, then you can solve for distance or acceleration. In this class, because we don't need calculus, you will always be missing one variable. Okay? You'll always be missing one variable to solve for because we don't do calculus. If we did calculus, then you could be like, let's arrange the equations, do a derivative or an integral, and we'll come up with it. But in this class, you will always have one of these things minus 1. One of these things minus 1. One of these things minus 1. You only have one variable to solve for. But what this represents is if you have initial velocity and final velocity, and you have distance, you can solve for acceleration. If you have initial velocity, final velocity, and you have acceleration, you can solve for distance. Or if you have initial velocity and acceleration and distance, you can find out the final velocity. Yeah. You never need to use this, but it's a fun little shortcut. Other questions? Okay. So imagine there's a cliff. And on the top of the cliff, there's a Patrick? Oh, that looks like Patrick Star? Okay. At the top of the cliff, there's a Chase. And Chase has a ball. And Chase is going to drop the ball. He's looking down, he's like, wow, that's a big, tall cliff. He's going to drop the ball. And he's going to drop the ball at time equals 0. Make sense so far? At time equals 0 seconds, what is the velocity of the ball? 0. How far has the ball traveled? 0 seconds. 0. That's convenient. And what acceleration will be moving at 0 seconds? Meters per second squared. It hasn't got a chance to do anything, so the bottom of that fraction is still undefined, but it's still going to have an acceleration of -10 meters squared. So good? Now, what formula do we use for all these things? We'll get to that at time equals 1. Opposite. Now, at time equals 1 second, we're moving a little bit. What is the velocity at 1 second? -10 meters per second. Hold on, Mr. Byers. What formula did you use to find that? Good question. The change in velocity is equal to acceleration times time. An acceleration of -10 and a time of 1 second. Capiche? Give me a thumbs up if you don't know where we are right now. Okay. By the way, the shrewd among you are doing this diagram because you'd be like, refer back to it. You can memorize it if you want. You can watch a video if you want. But this diagram is pretty handy. Okay, so that's the velocity. The distance. How far has it fallen after 1 second? Yeah, there's a temptation to say 10 meters. but it's not. The formula that we're going to use for distance falling is the free fall formula. We dropped it, therefore it was in free fall. It didn't get initial velocity, it didn't get thrown, it didn't get pushed, and we're ignoring air resistance, so the formula we're going to use is e squared. Oh geez, back row, can you see my numbers? No. Okay, I'm going to make them bigger. Forgot back row way back there. Okay, so now we're at time equals 1 second. Our velocity is now -10 meters per second. Is, we don't know. And because we're using d equals 1/2 at squared, and the formula used for v is vt. Does that help? Okay. Oh, and that's the ball right there. So, how far has it fallen after 1 second? 1/2. Gravity is -10. T squared is 1 squared. So 1/2 times 10 times 1 squared is 5. It has fallen -5 meters. So far, so good?
This is fantastic.
I'm glad you enjoyed this. Okay, so I'm seeing some bored faces. I'm not seeing a lot of confused faces, but I want to make sure are there any confused faces out there? Give me a thumbs down if you're not with us. Ryan's got a confused, oh, it's a bored face. That looks more like a bored face. Okay. Okay. How did D get what? D got negative because gravity's pulling down at -10. For the purposes of our discussion, down is going to be negative, up is going to be positive, to the right is going to be positive, to the left is going to be negative, and then when we get to circular motion, counterclockwise is going to be positive, clockwise is going to be negative. But we'll worry about that in over. Okay, shall we move on? Oh, question.
Why are we? Where did the delta v equals come from, and where did we use it?
Good question. It comes from this formula that acceleration or gravity will accelerate something, change its speed by -10 every second. And we used it here to determine how fast it's moving at 1 second. Other questions? 2 seconds? What does something become after 2 seconds? Orange. Okay. So, at 2 seconds, the ball is right here. It has got larger because people are looking at it in the backyard, or in the back of the room. There we go. So now the ball is right there, and t is now 2 seconds. How fast is it moving after 2 seconds? It was -10, now it's -20. So every second, gravity makes something faster by 10 meters per second. Okay? So after 1 second, it's traveling -10. After 2 seconds, it's traveling -20. After 3 seconds, we would expect it to be traveling how fast? -30. After 4 seconds, how fast? -40. Ignoring air resistance. Air resistance kicks in at about -10, -15 for most objects. So ignoring air resistance, which we will ignore until we do parabolas, projectiles, after 2 seconds, our formula is still delta V equals AT. So 2 seconds times -10 is -20. Capiche? Okay. Next, using the same formula for distance that we used before, how far has it fallen after 3 seconds? 40. 40 meters. 4? 20? -20. If you think it's -20, raise your hand. And you would be correct. So the formula is still D equals 1/2 AT. My pen is dying. Oh well. D equals 1/2 AT squared. Formula is still that. So 2 seconds, 2 squared is normally what? 4. 4 times 10 is normally 40. Times 1/2 is normally 20. But Mr. Byers, that means it covered 3 times the distance. Yeah, it did. It's speeding up. So it covered 5 meters here, and it covered 15 meters here, which is cool, because it is speeding up. Next. At 3 seconds, the ball turns red. And it's way down here. And it needs really long smoke trails. There we go. Okay. T equals 3 seconds. Okay, so now the thing's been falling for 3 seconds. Gravity's been acting on it the entire 3 seconds. How fast is it moving at the end of those 3 seconds? Negative 30. Again, the formula is still delta V equals AT, and the distance formula is still going to be the freefall formula, 1/2 AT squared, the triple F. So how far has it fallen in 3 seconds? Excellent. It's fallen 45 meters, so now it has a displacement of negative 45 meters. 3 squared is 9, times 10 is 90, times 1/2 is 45. It's fallen 45 meters after 3 seconds. And the formula goes on and on. If we ignore air resistance, eventually it's going to hit the bottom of something, but it's just going to keep falling and falling and falling. It's going to keep falling. It's going to keep getting faster by 10 meters per second. It's going to keep falling with a distance equal to 1/2 AT squared. Make sense?
What happens if Chase jumps off with the ball?
It depends on if Chase has air resistance or not. If Chase jumps off with the ball and neither of them have air resistance, he will also be traveling at negative 30 meters per second after 3 seconds. Yeah, exactly. Yeah, you've all jumped off a swimming board, jumped off a diving board or a swimming pool and thrown something, and for the moment it travels with you, traveling the same speed, which is why I have a lot of trouble with video games when you shoot a rocket or a bullet or something and it doesn't travel with you. It doesn't have its initial velocity, or a ball or something. Fun fact, there was an article about 10 years ago about why video games don't follow physics, and the conclusion the article came up with would be, it would just be too hard for people to understand. You've all played those games where you're sliding to the side and you shoot something and it's back here, it travels that way. In reality, it would travel with you, but we're going to get to that when we talk about inertia and forces. Okay. If you're comfortable with this, give me a thumbs up. Okay. Now with the time remaining, we're going to do something a little bit different. We're going to throw the ball. Does Chase throw the ball up or throw the ball down? Is he going to throw the ball up or throw the ball down? Up. Chase is going to throw the ball up. Okay. Chase is going to throw the ball up at t equals 0 seconds. And how fast are you going to throw the ball? 20 meters per second. Chase is going to throw it with an initial velocity. Guys, I realize we're not going to finish this today. We're going to pick it up. So I'm just going to plant some seeds. Things get a little more complicated because now we have an initial velocity. And our change in velocity is still going to be AT. But we're going to have an initial velocity, so our final velocity, I think this is a different color. Yay! Final velocity, not delta V, just VF. Our final velocity will now be the initial velocity we started with plus the change. So now every second we have, our final velocity is going to be our initial velocity plus our change. Does that make sense? So Chase is going to throw the ball up with a positive velocity of plus 20 meters per second. And I forgot we have someone in the back, so we'll make it really big. T equals 0 seconds, V equals plus 20 meters per second. But I'm going to put a little notation here. I'm going to say V at 0 seconds, V naught. V0, V naught. How much money do you have? I have not money. V0, V naught. Okay, so our V naught, which is V at 0 seconds, is 20 meters per second. Our distance is still 0 meters because he hasn't actually let go of it yet. Now, and the ball is right there. He hasn't let go of it yet. Here's Chase. Chase is like, I got a ball. Okay. At time equals 1 second, at t equals 1 second, where did the ball go, up or down? It went up. Now here's where things get interesting. Time equals 1 second, our velocity, v1, v at 1 second, this is 1 second, is what?